Now let's be specific. This was actually the generic part of discrete probability theory. Not quite true. We'll go a bit more generic at the end of the lecture again. Now I've defined the two concepts or three concepts: random variable, density, and distribution function. Now let's get that into play in some more real-life phenomenon. For instance, the classic binomial distribution. There are many such specific distributions that are in a way designed or invented or discovered, in a way you should say, because they have been there all the time. But at some point a few hundred years ago, someone realized that they were there, some mathematicians, and found out and put them into formulas that, because of course they've been there at all times. The binomial, the hypergeometric, and the Poisson. We're going to meet those three, but there are hundreds out there. But these are three important ones. The binomial. That's the coin-tossing probability model, right? Coin-tossing random situation model. There are many naive ways of saying it. The basics of it is that you are dealing with something. Whenever we say binomial, think of coin tossing, right? It consists of individual experiments, each of which have two possible outcomes. And we use generic words like success or failure. Plus, minus, 0, 1, whatever, heads, tails, live, die, if you go to clinical experiments. And failure, if you're in the production industry, either it works or it doesn't work, right? There is a whole branch of statistical research in the biostatistics area, which is coined survival analysis for the same reason. It's a pretty good thing to be doing research in, to the benefit of all of us. In engineering, that's called reliability theory. And reliability, lifetime can be a computer, and it can be a human being. Is that a question or a comment?
No, I've broken my collarbone, so I have to move it sometimes.
That's perfectly okay. I hope you'll be fine. And then we toss the coin. I mean, you could toss it only once. That's fine. That's also a binomial. Then it's called a Bernoulli. But usually we have more than one throw with the coin. So it's a repeated setting, doing the same binary experiment again and again. If you do it independently, then the probability distribution of the binomial appears. The thing is, we decide for some reason that what we're interested in, after having thrown the coin 10 times or 20 times, the only number that we are interested in is the number of successes. We don't care about the order in which they came. You could, of course, in other contexts, you could care about that, and then it's something else we need to be dealing with. But when we decide that the only thing we're interested in, the random variable of this random system that we're interested in, is the number of successes out of the n coin throws. Let me see. This means that we are going to assume that it's not necessarily 50-50. Right? We're going to be slightly more open-minded here in the model. It could be an unfair coin. It could be, if we test survival among patients, of course, we have to deal with that the proportion of survival could be anything between 0 and 1, basically. So we need a model that can deal with all sorts of probability levels. And let's say if we have n equal 4, for instance, what are the possible outcomes here? I didn't get the time to calibrate this one. I need to work on that. It's not really perfect for me here. We can see 0, 1, 2, 3, or 4 possible outcomes, right? That's the possible realizations of such an experiment. If you throw the coin 4 times, there are 4 possible outcomes, right? 5, thank you, possible outcomes, 0 to 4. Thank you. Good. What is the probability of seeing exactly, and I'm not going to give you a full mathematical proof, but I'm just going to try to hopefully give some words that can make sense of this formula. What if we are interested in asking the question if we have exactly 2 successes out of the 4? What should happen to get exactly? I should go, I'll have something else. I'll go for 3. That's better for the example. What should happen to get exactly 3 successes? Well, then 3 times it should be a success, right? There's a probability P to be a success once, P to be a success twice, P to be a success the 3rd time. And then one of the 4 times, it must be a failure, right? P was the probability of success, so 1 minus P. And in fact, we could go, this is actually 4 minus, this is x, and this is, the 1 here is 4 minus x, right? I'm trying to explain this number here and this number here. That's one part of the formula. The thing that I didn't yet cope with in my attempt of putting probability of x3 is that there is more than one way that I can get 3 successes in 4 throws. So we have, at least when we are going to think about the formula, we need to think about this order that we have. I mean, in the proof of the binomial formula, we would need to think about the fact that I could have success, 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 failure, S, S, failure, S, S, F, S, S, and F, S, 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 right? Exactly 1 failure could occur at 4 different positions, right? So I actually collected those 4. All 4 of them have 3 successes and 1 failure. So the probability of each of these 4 is the same, the one that I already put on the screen, right? I just have to add them up, because it could be either this one, or that one, or that one, or that one, right? Each of them could happen. So I have to add them up. When I add 4 equal numbers up, I can do it by multiplying by the number of times that they are there. So I multiply by the 4 to get the real probability of getting exactly 3 successes. And this counting here, that's a combinatorial challenge. That's a mathematical area of, what's it called? Combinatorial science, you know what I mean. Luckily, someone solved that challenge for us. And we're not going to prove that now, but now we've seen an example. Someone solved that challenge and made a formula to tell us how do I generally find out how many times can I actually pick out 1 out of n or x out of n. Because if I want to use this formula for n equal 100 and x equal 30, right? In how many ways can I have 30 successes in a sequence of 100? Whoa, if I could start doing this exercise, it's going to be, I'm going to have a long day, right? S 30, F 70. Oh, next one. S, and like that. I'm having a speaking problem also, so I'm pretty good at those sounds. We don't have to do this, so This is called the binomial coefficient, or in R, it has the name choose. Choose, and you would go, it's really poor with this, it's need to fix that. You would go choose n comma x, like this. And here's the formula. These are factorials, as you know. In 3 factorials is 3 times 2 times 1. Right? So here's the formula, and we can work with it. The formula itself is in R also, I'll show you in a second. Let's try to play with it now a little bit to get to know it a little better. Let's look at this first, and then I'll jump into the R code afterwards. Let's try to have probability of success only 10%. Let's try to do it 30 times. Let's try to now do it sort of manually or by hand in a way, if you want. I could sample, to use this sample function that I knew from before, I could sample between the 2 possible outcomes, 0 and 1. And I could do that 30 times. And I could have 90% probability for the 1 and 10% 90% probability for the 0, the first one, and 10%, that's the P, for the 1, right? So 10% for success, 1. 1 is success, 0 is failure. And then we could look at the numbers. Or I could use the inbuilt R function to do exactly that. Here we are. I had 2 successes here. What if I do it again? I can do it again and again. 3, 4. So with only 10% success rate, that's a bit like applying for research funds in Denmark. You spend 30 years, your whole research career. You submit 1 huge project application each year for which you spend months and months of hard work. And here's how many times in life you're happy. I'm going to get a new job, I think. Anyway. This is exactly what R has prepared to us in this function. R for random, binom for the binomial distribution, right? They made a randomization of binomials into an inbuilt function. And here I just do 30 throws, 1 time, but just have a look at how easy we could do more large-scale computations, even on a small computer just standing here in this little closet here. How about doing 1,000,000 times doing 30 throws with a coin? Try to do a little consideration how long time you should sit a Friday afternoon to do that. 30 times, and then times 1,000,000. This is how fast this little thing in this little closet could do that for us. So consider how, if you have a real good computer, get a feeling of the impact of this, of what this can do for us. How rapidly we can investigate large-scale experimentation simulations to tell us hardcore stuff by this. That's pretty strong computational tool. We're going to learn more about that. Let's see. We're going to do the exercise. Let's try to play around with this a little bit. So let's read this story. It's a call center, phone company. Customer satisfaction is in focus. They want to be a bit formal about how often they manage to correct the errors they get reported. So now we make an assumption about this random system. Now statistics is often about finding out about those numbers, but for now we are playing around with learning probability. So we'll get to the stats part in a couple of weeks from now. Now we assume that we know the system probability-wise. We don't know what's going to happen, but we know the probability of what's going to happen. That's the assumption. We believe, maybe you see it like this, historically, the company has seen that in 7 out of 10 cases, in 70% of individual error cases, they manage to fix that on the same day, right? So they have a success rate of 70% by this measure. The measure is, can I deal with it in one day, within the same day? Either I do it or I don't. So that's the feature we're looking at. And it's there twice, nevertheless. Now here's a bit of stepwise, everything is there in the same slide, but still, when you're meeting now, in the afternoon, later on, in the exam, in your life later, engineering endeavors, you will meet real-life phenomenon. You won't meet concepts like when you're in a company doing business. You won't meet a real life telling you, here is an x, the x has a binomial distribution with n equals 7 and p equal 0.7. Could you please tell me what is the probability of getting exactly 4 successes tomorrow? That's not the real life that will meet you. You'll meet a boss that's telling me, what the heck am I going to do now? Well, we're going to find out. I don't even know. I don't remember probability, and I don't care about probability. Just tell me what to do. So you have to identify those model structures that you can work with as the engineer. It's your job to look at the real-life phenomenon and put it into formulas, that meaningful formulas, such that you can work with those and give meaningful answers back to the real-life setting that you're a part of. That's modeling, right? And you're the guys who are going to do it. So when some story meets you and some question hits you, you should identify the model. What's the relevant random variable to talk about here? Well, it's not the most complicated of systems hitting us here. I think that the relevant thing would be to count the number of corrected errors in a day. Whoa, great. That's the first step. Now we have formalized. Then I think, if I think about this real life that is hitting us, I just maybe I make some assumptions. I make assumptions of independence. Maybe that's not correct, but I make that assumption. Then actually, my theory and my education tells me I think I can model this real-life phenomenon by a binomial distribution. Whoa, now I'm on track. Now I have the model in place. Now I can start answering real-life questions with my model. For instance, what's the probability of getting exactly 6? It would be like this. Now I'm actually confused a little bit. I think there isn't there an information that we lacked so far? Yes, here it is. Should have, of course, to make sense, we should already have sort of had that like this. So that's the setting. For now, let's assume we get 6 calls in a day. We have also models that can deal with this number being variable, but for now we consider it's a conditional setting, right? What if we get 6? What's the probability of fixing them all? Should we try to answer that? Do we actually get some... no, so let's try to answer it. What would be the probability of getting all of them correct here? Or rather solving all of them? It's a binomial probability, but it's one of the easy ones. What would it be?
0.7 to the power 6.
0.7.
About 12%.
And you already did the computation. Let's see. Well, if you looked, it was here. 12%. Also note that it could also be found in an R function, which is the implementation of the binomial probability formula that I showed you. That formula has been implemented into the D for density, binom function. And if I add in the n, that's the 6, that's the size here, that's the n. I want to have all 6 of them fixed. The probability is 0.7, and I hope it gives me the same answer, right, in this case. You could also, here's also a bit of, now we're in the, would be quite easy to go like this. I could go 0 to 6, and here they all are. That's the 7 different probabilities, so from these 7 I could answer anything that would hit me now on the next slide, right? For instance, what hits me? Is something related to the distribution function. Because I only gave you the density function so far, the probability density function for the binomial, explicit formula that we can use for such probabilities. Well, all the same, we have to fix what the setting is and all, but then at the end of this question, we have to find this probability. It could either be done by adding up, let's try. Of course, the answer, I could go sum of, I go this one, I go the sum of, what was it, less than or equal to 2? That was the probability we were aiming at, right? So I could take 0, 1, 2, that's the first 3 down here. That's actually these 3. And I add those 3 up. Either 0, or 1, or 2. That's what I do in my R code up here. I add those 3 numbers up, and I get 7%. Right? It's the sum of these, very small, and 1% and 6%, so that's around 7%. This probability, or the distribution function, that's called P, funny enough, P for probability. In a way that could be used both places, but that's how the naming is, actually. That's the naming in R. So the P binom is the distribution function for the binomial. So that's this aggregated probabilities. If you put in those, you can see it adds those numbers up. If we go P binom between 0 and 1, I meant between 0 and 6. You can see it increases slowly. I could also plot it, but let's look at the numbers. And at the end, it adds up to 1. Probability of being less than or equal to 6 in number of successes out of 6, that's 1, right? So that's the 2 probability functions that we can work with to be on top of the situation for the binomial. That's the binomial. Whoa, and then I almost forgot my Kahooting because I forgot, so here we are. We have a leader there. So, it says 0, 1, 2, 3 here. 0, 0, 1, 2, 3. Difficult to see. Oh, you're being challenged. Well, it's better. It's if we take the crowdsourcing approach, we had the right answers. It's getting difficult, more difficult now. And I realize you have very short time here, so you're stressed on time, for sure. Let's see. We had a change on the scoreboard. Let's have the break. So 15 minutes, 1 minute over, we'll start again.